Hey there, and welcome back. Let's continue our discussion of expression evaluation or predicate evaluation to be precise inside PostgreSQL. Okay, what we will see now in the coming minutes is a repetition of the phrase of the observation that we have made so many times already in this lecture. It's a red thread that runs through all discussions of the DB2 lecture, but also of the implementation efforts regarding relational database systems. Even very small gains, very small optimizations may add up and lead to significant savings when we are processing the same expression, the same filter, the same predicate over and over again for each of the scanned rows, like millions, tens of millions of times. Every little thing that we can gain there is welcome. And it's the same with predicate evaluation. What you will find in PostgreSQL is so-called heuristic predicate simplification. So somebody has specified a predicate, maybe in some convoluted, rather complex way. Before PostgreSQL will consider evaluating these complex predicates, it tries to apply simplification rules that reduce the size, in this case, the number of Boolean operators that you will find in such a predicate. Every Boolean operator that I can save means probably some opcodes less in the interpreted programs that I will have to evaluate for each of the rows. So everything I can remove there is actually a gain. So what we will find inside PostgreSQL implemented is partial evaluation that says, hey, this is a Boolean expression that you have specified in one of your predicates in your queries, but I can evaluate these expressions at compile time, at query planning time, and reduce them already to true or false. This might sound silly to you, because why would anyone ever enter such a simplistic predicate, such a constant predicate even, in a query? But not all queries are actually authored by humans. Some of queries, maybe most of the queries on this planet, are being constructed by programs, by web forms and whatsoever. And I've brought examples with me in the next few minutes. So then it might make sense to try to evaluate certain pieces of predicate and see whether we can reduce it to true or false even before query evaluation begins. Then, of course, we will apply basic identities like double negation can be removed, or distributivity laws that we can apply. So here you can see that we factor out the p that occurs in both of these Boolean subpredicates. We could factor it out and evaluate it once only and rewrite the predicate to use less Boolean connectives. Okay. Then we might see duplicate clauses that can be reduced, and we can apply rewrite rules to Boolean formulas that are well known, and that might open up other simplification avenues, opportunities for us. All of this is found in the heuristic predicate simplification of PostgreSQL. I'm underlining the heuristics here because these are simplifications of predicates that are assumed to be beneficial. They will probably simplify the evaluation at runtime, so let's apply them. What's not taken into account here, so let me rephrase it, it's not considered yet how costly these subpredicates may be and how selective they are. So selectivity is an entirely different story. We have seen the notion of selectivity in the last video already. It will pop up again when we consider the evaluation of queries using indexes. So what we are talking about here is heuristics. So simplifying rewrites that will probably yield a gain. Let's switch over to the interactive SQL terminal and see whether we can find such simplifications in real SQL queries. All right, so this would be one of such SQL queries, and you see that the predicate that I've specified here is really convoluted and actually super complex. It could be simplified. Why at runtime perform all the threefold not negations if we could already remove then at query planning time and rewrite the predicate to make it simpler, less interpreted opcodes to consider during query runtime. So what PostgreSQL, for example, would do is, of course, remove this double not here. So a not P is just P. We can get rid of two of these nots very easily. We can also get rid of this third not if we apply De Morgan's law and turn this and into a disjunction, into an or, but then negate the two subpredicates here. And let's see whether PostgreSQL understands its Morgan's law. Okay, it looks like it. This is the rewritten predicate in the planned query plan, no evaluation yet, just the simplified predicate in the filter slot of our sequential scan operator. Okay, as you can see, no not has survived. The and has been turned into a disjunction. And indeed, the equality has been turned into an inequality, and this less than operator has turned into its negated equivalent, the greater than or equals operator. All right, so this should have the same semantics, but it uses less Boolean operators. We have lost this stack, this nesting of the three nots here. Okay. This would be a different example, an example that is relying on factorization. You see that this Boolean factor here, this Boolean subexpression is occurring twice, identically occurring twice in the two branches of our overall disjunction here. And we could just apply distributivity of and, or the inverse of distributivity of and, to really factor out this now marked, this orange marked subexpression evaluated once only and save evaluation time at runtime. So let's see how the rewritten predicate looks like then. Okay, right. So okay, yeah, this is the factor that has been removed. It's considered once now only. It will be evaluated once only, and you see that there is the parenthesized disjunction here that is connected to the top level and now. All right, so that's distributivity of and has been exploited to simplify the expression. Okay, so if some of these expressions have already looked strange to you and you thought, hey, these are artificially constructed to make a bogus point, then I would like to remind you that indeed many of the queries out there are not being specified by SQL experts, performance experts, but that they are constructed automatically. For example, by users that fill in a web search form. Users that are never aware of the fact that they're filling in a form will lead to the construction of a SQL query, in this case a SQL predicate, behind the curtains. And the generated SQL predicate might look silly indeed. So let's consider this example where we use a web search form to query the ternary table. The ternary table has fields A, B, C. In this search form, we can specify values for the A and C columns. So any value entered into the A and C fields here will be used in an equality test on the A and C columns of table ternary. If users choose to not specify, as is the case here, to not specify a particular value for column C, for example, then the web search form, the front end, the web front end will indicate that by setting the value that's looked for here to null. All right. So this is how this web form communicates to the backend. The user has not entered a particular value. The null should be considered as a wildcard. Any C value is fine. Okay, so this covers the first 2 points here. What's the query? What's the SQL query that we have to construct in the background? Well, it would be this query. Of course, we would scan the ternary table and we would, the backend would produce all the information that's in the ternary table for the front end to display in some appropriate form. But the predicate is the interesting part here. All right, so the value entered in these two search fields, let's assume that they end up in these two variables :A and :C here. And they appear here again. So the value entered in the A search field will be represented in colon A. The value entered in the C search field will be evaluated as colon C here in our query. And to implement the wildcard searching logic, this would be the query that is being constructed. All right. So a row would qualify if the A value has been specified and it's indeed equal to the A value of the current row. But it's also okay if the A value is null, so it has not been specified. In this case, the A value is any A value is fine. The null indicates wildcard behavior. Okay, so if A is indeed null, then this would be true. The whole OR would yield true. Okay, so regarding the A column, this would indeed implement the wildcard behavior. Any value would be fine. And the same logic is, of course, being applied to the C column here. And if both of these search criteria are fulfilled, then the row may pass, and it's one of the rows that has been accepted by this web search form. Okay, so what I'm describing here is really a regular setup that has been implemented a million of times already in database-backed websites out there. Let's switch over to the terminals and see about the consequences. So here we go again. This is the query, the backend query that is being performed on behalf of the web search form. When we click submit, this will be the query that is being evaluated. All right, so let's just simulate that the user has entered a value in the A search field, but has entered no value in the C search field. So any C value is fine. Null is to be considered a wildcard. All right, so let's set the search parameters here. Okay, and then we would evaluate this particular query. Sadly, this Boolean expression is rather complex, but as you can see, the simplification built into PostgreSQL, the predicate simplification, will cut down this rather complicated disjunction or conjunction of disjunctions into something simpler based on the now current bindings for our search parameters. So let's see what happens here. Okay, so that's a filter that looks much simpler to me. All right. So because C has been null, this has been evaluated to true. Okay, so the entire predicate has been evaluated to true, the entire disjunction here. And a conjunction with a true predicate, with the true value here, is actually superfluous and can indeed be removed. So the whole AND branch and the whole predicate here can be removed. We know that A is 42 when we plan the query, so this is false indeed. This is false indeed. So any value in a disjunction with false is just that particular value. So all that remains is indeed the search predicate TA equals 42. That's the best, the most compact rendition of a search predicate that we can hope for if the user enters these particular values in the search form. So let's see if the A value is also missing. The user has just clicked submit and has not specified any filtering criteria. That would be the new submission and the new planning of the backend query for this search form. Indeed, no filtering at all. No filtering at all. Play the game again, fill in the null values for A and C into these predicates, and then see that the whole thing here will evaluate to true and the predicate has indeed been removed. So if we are picky again and are looking for particular values and submit a fully specified search form, then this would be the outcome. It would be just the conjunctive predicate that we had to expect here. So predicate simplification can really make a difference and can really be a real gain when it comes to automatically constructed queries. So let's switch that back to null here. Okay, but these heuristics, the predicate simplification sometimes it's not enough. Sometimes we really would need to consider the real evaluation cost of the pieces of our predicates. So if there are some sub-predicates that are more expensive to evaluate than others, then the system should try to make good use of that. And I brought one example with me here in which we are filtering a version of the ternary table. You see that I'm considering a larger version of the table now just to amplify the effect that we are going to see here. And you see that I'm filtering regarding a disjunctive predicate. Okay, the two sub-predicates, the two clauses that are being considered in this predicate are string based. So this particular predicate, this predicate part is string based. You see that I'm looking at the textual B column carrying these strange MD5 hash values. To that column I'm applying a string function, the btrim function, that will cut these characters specified here. These characters will be cut from the left and the right part, from the prefix and the suffix of that string TB. We will search for the 0, 1, 2, for all the digits, and we'll remove them from the start and the end of the string. That takes some time, and then we will start to count the characters in the resulting string and compare it to the length of the characters in the original TB string. So really quite expensive string operations here. Counting characters, manipulating strings, then counting characters. All of this takes its time. It takes considerably more time than just this very simple predicate. It's just a very simple modulo operation over integers and then a comparison with a literal 0. This is a predicate that is probably way cheaper to evaluate. And I have indeed measured the cost for the evaluation of this predicate. It's indeed significantly different. So this would be the more costly predicate, and this integer-based predicate is the cheap part. And indeed, it makes a difference for expression interpreter in PostgreSQL, for example, whether we first consider this first more costly clause and then only later consider the cheaper clause here. All right, because we are implementing Boolean shortcut. Had we only considered this cheaper clause first, if its outcome is true already, the entire disjunction would be true, and we would not need to consider this super costly string-based clause. All right. So considering the cost of these sub-expressions, of these sub-predicates, actually could make sense, and an reordering of clauses or considering of clauses regarding the cost, cheapest clauses first, in a sense, could really make a difference. The bad news is this is not implemented inside PostgreSQL currently. PostgreSQL currently has no information about the complexity or the cost of the relation of this sub-predicate, and we will see that it will miss an opportunity for simplification there. Please be aware that this is not a discussion of selectivity. Both of these predicates are not very selective. They're really non-selective predicates. The difference that we will now see in the experiment is not based on selectivity. It's only based on the cost, or the evaluation cost, of these sub-predicates. Okay, so let's switch over again to the editor. And you see that I also brought a larger version of the ternary table with me. 2 million rows should suffice to demonstrate the effect already. Okay, so yeah, okay, so this is the version of the query on the slide, and you see that the costly predicate, the costly clause, is the first clause that we have mentioned here in this disjunction. And as things stand now in the implementation of PostgreSQL, indeed, the evaluation of this disjunction will first consider this costly predicate. All right, that's unfortunate, but this is how predicate evaluation is currently implemented inside PostgreSQL. So let's see how this performs. Let's evaluate it. All right, take some time. Okay, this system is really busy. Okay, it takes 8 8.5 seconds to evaluate this version of the query. As you can see in the plan, indeed, the order of the clauses in this disjunctive predicate is the same order as I have specified in this particular query. And if you would look at the threaded interpreted program that has been generated for this particular expression, then indeed the interpreted program would first consider this marked costly part of the predicate first. If you would rewrite this predicate in a trivial fashion and just swap the order of the clauses, now the first integer-based cheap clause is the first clause in this disjunction, then we would evaluate this thing again, and we would see a difference, a stark difference. 2.6 seconds instead of 8.5 seconds. All right. So the Boolean shortcut that could be applied here in a very cheap fashion, because we really knew something about the outcome of this particular predicate when we only implemented or evaluated this marked sub predicate. This really brought us some advantage, some real gain. Okay. So in an ideal world, PostgreSQL would be informed about the expected cost of the relation of this clause compared to this clause. This is not currently implemented in PostgreSQL, and we miss something here, some optimization opportunity. All right. This is not to say that PostgreSQL is completely uninformed about the expected cost of the relation of predicates. And this is where selectivity will come into play again. Of course, there is a very versatile infrastructure inside PostgreSQL that considers the selectivity and thus the cost of queries that have filters built in. But this is something that we will consider in the upcoming chapters. And I hope you will be around then.